Welcome to video number 4. In this video, we're not going to try to cover any new material. Instead, what we're going to do is to try to address questions that have come up in class as we have worked on the first computer projects. And we just also want to take this opportunity to make sure that everybody understands exactly what those what the first computer projects are. So for project 1, that is, and by the way, now before I even go any further, let me make sure it's clear that for all of the computer projects, you're going to be producing plots, and on every plot that you produce, you should graph both the analytical solution and your numerical solution so that we can compare them and get an idea of how accurate your numerical solution is. So just keep that in mind. For all of these projects, you're going to produce plots that will have two graphs on them, the numerical solution and the analytical solution. Okay, so in project 1, you're writing a code to solve Laplace's equation with the following boundary conditions: v of 0 is equal to a, v of L is equal to B, and the number of nodes is equal to n. And as we've said before, you should write your code in such a way that you can easily vary A, L, B, and N near the top of your code, and that will it will be unnecessary for you to make any other changes in your code when I request you to change one of these 4 parameters. Now, for project 2, once you have finished project 1, then project 2 will be to modify the code you have for project 1 so that it can handle these new boundary conditions. V of 0 is equal to A, and dv dx of L is equal to B, and the number of nodes is equal to n. So in this case, you'll have the Dirichlet boundary condition at the left boundary, but the Neumann boundary condition at the right boundary. Now the question arises as to how you should implement that Neumann boundary condition on the right boundary. And I want you to do it in 2 different ways. The first and simplest way will be the following. Now I'm assuming assume that node n is at x equals L. So in other words, the nth node is the node on that right boundary, and so the first and easiest way to implement this boundary condition is to say v n minus 1 excuse me, this should actually be Vn. This is certainly a little tedious. Okay. So Vn minus Vn minus 1 over delta is equal to B. That will be the last equation in your system of equations. That will be the last equation, and this is one way of implementing this second boundary condition here. I'll call this 2 and 1. We've already discussed how to implement the first boundary condition, but this is we'll call this the first order method. So this is the first order method. It's very simple. You just approximate that derivative at node n by Vn minus 1 over delta and set that equal to B. And then the second method that I want you to try after you've considered that first method, then I want you to try the following. We're going to go back to our notes and you will recall that in our notes we had this formula right here. This second formula was this was a general formula for the first derivative at node k, and so we will use this formula to find another way of implementing the Neumann boundary condition at the right edge of our boundary. So we have let's see if I can copy and paste this. We don't need this first part about the second derivative, so I will erase it. Obviously, I should have chosen a larger eraser, but we're almost done. Okay. So for the second method, I want you to use this formula, which is more accurate, a more accurate way of approximating the derivative at node k than is the formula we had in part A. And so let's make sure that it's very clear how you're going to use this formula. Okay, now remember we're implementing the boundary condition at node n. So first of all, k, this formula as it states right here, this is for node k, where k can be a general node. now we're going to pick a particular value for k. So pick k equals n. And likewise, we can pick I and j as well. And it seems like to me that the reasonable thing to do is to pick I equal to n minus 2 and j equals n minus 1. So in other words, if you think of your problem domain as being like this is the x direction, and here's x equals 0, here is x equals L, then we're looking at these last three nodes, node n minus 2, node n minus 1, and node n. And we want to evaluate that derivative, dy dx, at node n. And we don't want the expression to involve any locations outside of the mesh. But it is okay if it involves nodes n minus 2 and n minus 1. So that's what we'll do. Okay? So let's see what this will give us. We'll have dy dx at node n, because remember, node k now is node n. Okay, it will be xk minus xj. Now remember, this is node I and j and k. So xk minus xj will simply be 1 delta. And in the bottom we have xi minus xj. That's negative delta, because as you can see from the figure, xi is at node n minus 2 and xj is at node n minus 1. So xi minus xj is actually a negative number, and it's negative 1 delta. Xi minus xk is negative 2 delta. And then f of xi becomes v sub I, which is v sub n minus 2. Now the next term will become xk minus xi, that's 2 delta, over xj minus xi, that's delta, and xj minus xk is negative delta. And then we have f of xj, so that's v sub n minus 1. And then the final term will be plus, now as is noted here, that 2xk minus xi minus xj could be written, as you can see right here above, it can be written as xk minus xi plus xk minus xj. And let's think about it that way. So xk minus xk minus xi will be 2 delta plus xk minus xj will be delta. And then in the denominator we have xk minus xi, which is 2 delta, and xk minus xj, which is delta. And then f of xk, which is v sub n. Oh, and we're calling the function v here instead of y. So we have dv dx at node n is equal to this expression, and if we simplify that, we get dv dx at node n is equal to 1 over 2 delta times v n minus 2 minus 2 over delta v n minus 1 plus 3 over 2 delta v n. And remember, we want to be setting that derivative dv dx at node n equal to b. So our final equation for part B will be 1 over 2 delta v n minus 2 minus 2 over delta Vn minus 1 plus 3 over 2 delta Vn equals B. There's the equation that you will implement in Part B of Project 2. And please be sure that you understand how I obtained that, because I might ask you to do something similar to that on a quiz or a test or maybe even the final exam. So make sure you do understand how, if you were given a formula like this, how you could apply it at a particular node. Okay. Now, once you have done parts A and B for Laplace's equation, what you're going to find is that the results look exactly the same. And in fact, in both cases, the results will agree essentially exactly with the analytical results. Why is this? Well, it's because your solution is a linear function, and these approximate formulas that we're using for the derivatives are actually not approximate, but instead are exact for linear functions. It's only when we get to more complicated functions that these formulas for the derivatives begin to have some error. So when you do Project 2, parts A and B for Laplace's equation, you should get excellent agreement with the analytical solution. But now in Part C, what I want you to do is to repeat parts A and B for the equation d squared v dx squared plus k squared v is equal to 0. V of 0 equals a dv dx of L is equal to B, and number of nodes equals N. So you see that the boundary conditions now are the same as in parts A and B above, but now we have a different equation. Now you might wonder, well, what will that different equation do? Well, it doesn't change the first line of your matrix, because that is the line dealing with the boundary condition at the leftmost boundary. And notice that that boundary condition at the leftmost boundary, which is right here, that's exactly the same as above. And it won't change the boundary condition at the, or won't change the last line of the matrix, because the last line of the matrix deals with the boundary condition at the rightmost boundary of the problem domain, which is this boundary condition, and we haven't changed that either. It doesn't change the number of lines in the matrix either, because that's governed by the number of nodes. But what will change are all the lines between the first line and the last line, or the first row and the last row of the matrix. But it will be just a small change. All we've done here is to introduce that one extra term, k squared v. And you might wonder, okay, how am I going to incorporate that? Well, just remember that we are applying this equation right here at each node. So this is saying d squared v dx squared at node I plus k squared times v at node I is equal to 0. So you just have to keep in mind that you're enforcing that equation over and over at the particular node in question. So for row 2 of the matrix, you're enforcing that equation at node 2. For row 3 of the matrix, you're enforcing that equation at node 3. For row I of the matrix, as long as I isn't equal to 1 or n, as long as it's not the first row of the matrix or the last row of the matrix, to get row I of the matrix, you enforce that equation at node I. And if you'll just keep that in mind, then you will see that this k squared v term, all it's going to do is make a small alteration in the diagonal element of the row. And I think that with that hint, you should be able to finish this pretty easily. And then the last thing I want to say is the following. Okay, how do you get the analytical solution for d squared v dx squared plus k squared v equals 0, v of 0 equals a, dv dx of L equals B. How can we get this? Well, again, we can, as we did in class, we can let V of X equals C e to the px, and so then dv dx would be p c e to the px, and d squared v dx squared would be p squared c e to the px. And if we substitute these expressions into the equation, we get p squared c e to the px plus k squared c e to the px equals 0. So p squared plus k squared c e to the px equals 0. And there's only two ways this can be true: either p squared plus k squared equals 0 or c e to the px equals 0. But we don't want c e to the px equals 0, because if we chose that, well, c e to the px, notice that's this c e to the px, that we can see up there, that's v of x itself. So if we chose that to be 0, then we're saying v of x is always equal to 0. And yes, that would satisfy the differential equation, but in general it would not satisfy that first boundary condition, which is v of 0 equals a. So we don't want that possibility, and therefore we're left with p squared plus k squared equals 0, and therefore p squared is minus k squared, which means that p is equal to plus or minus I k, where I is the square root of -1. If you wish, you can say j as well, whatever you want to call it. So our solution then is v of x equals c1 e to the ikx plus c2 e to the minus ikx. That's one way you can write it, and that's fine, but it's not the most convenient way to write the solution. As you probably remember from your differential equations course, in a situation like this, you can also write the solution like this: d1 sine kx plus d2 cosine kx. And this is a much better solution to use. It's much more convenient. They're equivalent, but this is much more convenient to use. And of course, how do you find d1 and d2? You find d1 and d2, I'll say, use the boundary conditions to find d1 and d2. So now, to just briefly review, part C of project 2 is to repeat parts A and B, but for this equation. And whereas when you're solving Laplace's equation, you found that parts A and B both give excellent results, but when you use parts A and B, when you apply those two different methods for this equation right here, this is the wave equation. When you apply these two different methods for the wave equation, you will see that the second method, the method detailed in B, is much more accurate than the method detailed in part A. And so that's the point of doing part C. But you will have actually two codes to write here for part C. And so I hope that helps to answer some of the questions that have been coming up in class. And that concludes this fourth video. So good luck.